Hello everyone and good morning. My name is Mert Kesici. I'm a PhD student at Imperial College London and I'm working as one of the early stage researcher in the InnoCyPES project. And today topic is going to be privacy preserving load forecasting based on the smart meter data. And the content of the presentation will cover first the big data and its related issues in smart grids. And then we will be looking at an overview of data sharing concerns in smart grids. And then we will be slowly moving to the privacy concerns for the smart meters. And then a specific problem with the smart meters, the load forecasting problem. And then we will be investigating the privacy preserving data-driven algorithms, which are going to be federated learning and split learning. And then we will be discussing this application of these two algorithms to this specific problem. And then the main goal of this presentation is to introduce the privacy preserving algorithms and their application to individual smart meter load forecasting. So as you know, the modern smart meter collects data from a wide range of technical resources, and this data includes information from smart meters, phasor measurement units or remote terminal units, and SCADA systems. And this whole represents the incredible volume, velocity, and variety of data, which we refer to as big data. And these data streams are constantly flowing into the smart grid infrastructure, which are then used for different applications and purposes. And the aim of this big data analytics in smart grids is to harness this enormous data and turn it into actionable insights. And by using the big data, utilities can improve operational efficiency and enhance customer services and ensure grid resilience and stability as well. For example, the smart meters continuously feed data on energy consumption patterns, allowing for dynamic load balancing and weather forecasting. PMUs or micro PMUs monitor real-time voltage, current, and frequency across the grid. And these precise measurements are crucial for maintaining grid stability, like detecting disturbances and improving system stability. For the SCADA systems, they provide the operational backbone of the grid and enabling real-time monitoring and control of grid components. And the systems work in conjunction with the field measurements unit like RTUs and gathering data from substations and from other critical nodes in the grid. And we can then categorize this smart grid analytics into several layers and showing how big data translates into specific actions. For example, for the operational analytics, this includes the grid's overall performance, adaptive analytics for the predictive maintenance, and like visualization tools that help the grid operators manage renewable energy, forecast energy demand, and enhance resiliency. And for the enterprise analytics, big data helps with energy forecasting, asset management, demand response, and pricing analysis. And these factors are crucial for utility companies to balance supply with fluctuating demand and price energy dynamically. And for the customer operations analytics, like by analyzing the customer behaviors, utilities can segment customers and understand their energy consumption patterns and manage home energy usage more efficiently. And it also helps in personalized services and improved billing systems. For the event analysis, big data helps like identify, classify, and filter grid events such as outages or anomalies. And through these utilities can pinpoint the root causes and reduce downtime. And for the state and signal analytics, on a more technical level, these analytics handle real-time data from the grid infrastructures like substations, sensor signals, or waveform analysis, and it helps maintain optimal operation of conditions by identifying faults before they escalate into like more significant problems. And when discussing big data in smart grids, it's also essential to understand the significant challenges that come with managing and processing this information. And one of the major issues is data quality. And we might frequently encounter missing data or noisy data that has been corrupted or affected by various factors during the transmission of the data. And these gaps or inaccuracies in the data can severely affect the performance of the analytics or decision-making processes. And the second one is the lack of historical data. In many cases, smart grids are relatively new systems, and there may not be enough historical data or like the sensors to generate long-term trends and or reliable forecasting models. And this lack of data hinders the machine learning models and predictive analytics. Abundance is another problem. because we might face an overabundance of data where vast amounts of information are collected, but identifying relevant features or attributes is challenging. And proper feature extraction and selection, therefore, are critical to ensure that only meaningful data is processed from this vast amount of data. And another issue is the improper data management. And without proper data governance, like inconsistencies, irrelevance, or incompleteness in the data can occur. And these factors can lead to poor decision makings. And apart from these common data related issues, there might be also other concerns related to the data sharing. For example, in some cases, data collected by a single entity, stakeholder, or data owner might not be sufficient for a comprehensive data-driven application. And smart grids rely on diverse data sources, and without collaboration between the multiple entities, it can be incomplete, biased, and which can limit its usefulness. And even when relevant data exists and sharing it between entities can be a challenge, market competition may prevent companies from sharing data with one another. And likewise, data owners may see potential profit in keeping their data exclusive or might restrict access based on their business strategy or interests. And additionally, security and privacy concerns play also a significant role because with the increasing threat of cyber attacks and importance of protecting customer privacy, there is often hesitation around sharing sensitive grid or consumer data, and even though it could lead to an overall grid optimization. So in summary, while big data has the potential to transform the smart grid management, these data-related issues, like whether technical ones or policy and ownership concerns, must be addressed to unlock the full potential of big data analytics. And in this slide, we will be exploring some of the key data sharing concerns reported in the smart grids and focusing on the interactions between different operators and entities, and as well as the sensitive nature of certain types of data. So based on the reported studies, for the transmission system operators, the PMU data is considered critical energy infrastructure information, and the operating entities, the system operators, are careful to protect them. And some of the examples can be specifically seen in and specifically reported in US, as there are different, like more than one operators operating the grid, and they need to share data with others to create like certain applications, such as the, a big situational awareness monitoring systems. And the data sharing concerns are also visible between the distribution system operators when it comes to certain applications such as condition monitoring of certain assets that can be transformers or cables when the data is also rare in one of the system operators. When it comes to the multi-energy systems to operate these energy hubs in an optimal way, they also need to collaborate. However, entities might be reluctant to share their operational data. And another example, which can be the most known one, is the privacy concerns with the individual households with smart meters, which is also going to be the key point of this presentation. And some other examples can also be seen when it comes to the microgrids. Yeah, these are like an overview of the data sharing concerns reported in the literature. And then I would like to give you some like concrete examples reported in the literature with a little bit more details. And this table presents an overview of data sharing concerns, like categorized by the entity types. And it also provides the tools developed where they have faced these data sharing issues and respective measurements and the associated risks. So as you can see, the first four studies report the data sharing concerns among the transmission system operators. For example, the first one created an inertia estimation tool for a multi-area interconnected power systems, where each area are reluctant to share their local measurements, and the risk is stated as data privacy between the areas or the transmission system operators. The second one states that the cyber-related information are highly sensitive and rare as well. Therefore, a decentralized and privacy-preserving tool is proposed to design a cyber detection tool where a couple of transmission system operators are involved. And here, the cyber-related information is stated as bus measurements, such as the voltage, power, injections and flows, which are exposed to a cyber attack. And for the third and the fourth ones, the partial discharge identification for lines and defect detection for insulators are designed considering data from other TSOs, as the measurements in a single entity are not enough and rare. And moreover, this data, as this data might reveal the power system characteristics, they also went for privacy preserving approaches for this two specific problem. And if we move to the distribution level, the tools for diagnosing the partial discharge and insulation defects in switch gears are designed considering the data privacy and conflicts of interest between the system operators. And another reported study is for the failed diagnosis in 8 for the power transformers. Here, commercial competition is reported due to the highly privacy-sensitive equipment information among the rival distribution system operators. And here, the measurements are related to the transformers in the grid. And lastly, a voltage control problem based on the virtual power plants are also reported as a problem in the distribution networks. So the next one is the wind farm owners and operators. A couple of studies are reported, such as wind power forecasting, ice detection, and fault detection for the wind turbine blades. So the measurements are mostly related to the wind power generation and related to blade icing and the faults in the wind turbines. And it is stated that the most wind farms are unwilling to share their data, mainly due to the commercial competition between the companies. And the sensor data of wind farms or in a wind turbines often contain valuable information that can help maintaining a competitive position in the market, such as key parameters for tuning and controlling wind turbines for better health and improved performance. And also the situation is creating a so-called data island problem. And apart from the risk related to the data sharing concerns, it's also important to note that some of the studies also state that centralized learning poses risk of cyber attacks as well. So this is another reason of choosing decentralized approaches as well. For the electrical vehicle owners and EV charging stations or operators, EV charging discharging control problem and demand forecasting problems are reported, as the measurements related to the charging profiles, duration in the charging station, consumption pattern are the personal identifying information to protect the privacy of EV users. The privacy preserving approaches are investigated in 12 and 13 as well. And the next one is among the operators in multi-energy systems or energy hubs, where the heating, gas, and electrical network operators are connected to each other and try to operate this coupled grid in an optimal way. And in 14, optimal dispatch problem, in 15, load forecasting problem are investigated, considering the privacy limitations among these utilities. And it is stated that each utility would like to protect its operation and information, in a private. And last but not least, there's a well-known privacy issue with smart meter data. And a wide range of applications are reported, such as smart meter load forecasting, energy theft detection, non-intrusive load monitoring, and customer characteristic identification. And the examples can also be more examples can be seen in the literature as well. And the risk is stated as the leakage of individual data, causing personal identifying information. And as I said before, the focus of this presentation will be on this specific part with the smart meter data. So these are the corresponding studies published in the literature. So if you are interested to investigate the details more and more, you can just go to these specific papers. And we have investigated many different data sharing concerns among different data owners, but it is also important to note that, the generalization cannot be made for these data sharing issues, because the data owners or the operators might react differently, right, to data sharing concerns or to specific measurements. And the same type of data or measurements can be shared by some, but not by others. And data sometimes in one data owner might be already enough. And there is also one problem with the definition of the risks. The risks by sharing the measurements should also be stated and defined clearly. So we will now be talking about the privacy concerns for the smart meter, which is also like going to be our key data. As you know, the basic feature of the smart meters is that they are able to report the consumption values from a house. And this consumption data is basically the sum of all electrical appliances used in that specific house. And a daily profile of a house is obtained from the usage of these appliances, such as lighting, cooking, or washing, or whatever we have in the house. And when we see the total consumption as the smart meter output, it might not be directly visible when and how much of these different appliances are contributed to the load profile. However, with some specific techniques called non-intrusive load monitoring, it is possible to extract each individual appliance profile from this smart meter data. And of course, there has to be a certain amount of data that needs to be reported and with a certain sampling rate. And for example, on the right, this table shows what kind of information of an individual household from an individual household can be extracted for different reporting rates. And based on these reports published by the Energy Future Labs in Imperial, if the reporting rate is less than an hour, it's possible to extract a very detailed socio-demographic information, such as number of residents, like their age, even marital status, employment, and even health cases. And if we have a less frequent data, such as daily, dwelling characteristics can also still be extracted, such as the number of rooms, size, and location of the house. And because of the risk of revealing this personally identifying information, smart meter data is defined as private data, and its usage is limited by different regulations in different regions. So if you look at these regulations for customer protection, such as the smart meter data, in the past decade, countries and different regions throughout the world have developed many data privacy protection policies, and which serve as essential means to data privacy. And the following timeline shows some relevant policies since 2018, implying that the increasing concerns attached to the privacy issues. For the general privacy protection policies, the European Union's General Data Protection Regulation, GDPR, has become a global standard for data privacy, and which is approved for adoption in 2016 and was formally implemented in 2018. And based on the GDPR, many countries and regions have developed different policies aligned with it, such as you can see here, US, Canada, China, and South Africa. Therefore, it is evident that the countries and regions are paying much more attention to privacy issues in the era of big data. And for the privacy protection in energy systems, of course, like related policies still have a long way to go, because the main reason for this difficulty of such policy development is the conflict between social interests and the individual privacy. On one hand, data in energy systems are mostly recorded by advanced metering infrastructures with smart meters and support the better operation of the system. On the other hand, the consumers are afraid that their daily behaviors will be disclosed by this data, thus exposing their privacy. And this conflict mainly leads to the difficulty of developing a trade-off data privacy protection policies in smart grids and energy systems. To date, according to the report stated below, there are four main practices in Europe and North America to address like such trade-offs. The first one is the customer opt-out policy. The customers have the right to limit their data collection from digital energy meters, and even they can quit and retain the analog meters. And they have also option opt-in for demand management. Customers are encouraged, but not required, to allow fine-grained data collection through some incentives. And the third one is independent data storage. Like independent third parties are established to store the encrypted energy consumption data and then delete the data after a regular period. And separate monitoring and enforcement agency is the last option. A separate governmental agency is established to handle privacy monitoring and enforcements. So these are the four main practices in these regions. And I also would like to show you on how the smart meter deployment looks like over the years in the UK. And the UK government first announced its intention to mandate suppliers to install smart meters in 2008. And because a full smart meter rollout would enable customers to actively keep track of their energy usage to help reduce costs. And in turn, this would help raise consumer awareness and reduce consumption as part of the wider net zero strategy for reducing the impacts of climate change. And what we see is that between the first quarter of 2019 and third quarter of 2023, the number of smart meters in the UK more than doubled. And at the end of September 2023, there were around 33.9 million smart meters in the UK homes. And statistics indicate that the number of smart meters in the UK has steadily increased since they were first rolled out in 2018. And currently, according to the last report at the end of March 2024, there were around 35.5 million smart meters in Great Britain in homes and small businesses. And of these, 31.6 million were operating in a smart mode. And now, in total, 62% of the meters operating smart meters. So this is also a big amount of meters among the whole meters, right? So yeah, so what can we do with the large number of smart meters, right? And these diagrams outlines the key applications and techniques used in smart meter data analytics, which plays a pivotal role in optimizing grid operations and customer management. Yeah, the first section is load analysis, which involves tasks like bad data detection to identify erroneous or missing data, non-technical loss detection, which addresses energy theft or meter tampering, and load profiling, which helps in understanding the customer consumption patterns. Like the second section is the load forecasting, which is essential for predicting the future energy demands, and the load management focuses on customer characterization to better understand the segment users, and demand response program, which helps managing energy demand by adjusting the consumption during peak periods. And outage management is crucial for detecting and responding to the power outages. And data compression is important to reduce storage and transmission costs. And among these different applications, we will be focusing on the individual smart meter load forecasting problem. So in a most basic definition, the purpose of smart meter load forecasting is to forecast the consumption values at the next time step or the next time steps based on the historical observations. Of course, the input can be extended to different features as well, such as the weather data and calendar information, such as the day, month, and year of the year of the calendar. And within this presentation, only the machine learning based methods will be investigated, and therefore we need to design a proper machine learning model based on the data that we have and map the input and output properly. And then with the trained machine learning model, then the forecasting can be performed in real time. And we will be talking about the details in the next slides. And as a quickly, which applications benefit from the smart meter load forecasting, right? Once we get the output, which application can benefit from it? And it can be used for the demand side management programs, home management systems, and it's also an important input for the aggregate level forecasting, because it gives us fine-grained information, and it can also be used to transactive energy systems and for optimizing the electricity purchasing stage. So in this smart meter load forecasting, we have general approaches. Of course, they are going to be only machine learning based, and which can be categorized as centralized learning, localized learning, and the frameworks based on the privacy-preserving data-driven algorithms, which are going to be federated learning and split learning. And throughout the presentation, only the main architecture of these frameworks that can also be said the vanilla versions will be discussed. And the details about the communication networks or communication requirements are not covered in this presentation, and these are not modeled. So the first one is going to be the centralized learning. So for these frameworks, we can simply imagine we can simply imagine an environment as two parts. Sorry, and the server and the grid edge in a basic form. And the server or the cloud can be considered as the control center or a place where the data is collected and processed by the operators. And the grid edge or the grid side can be considered the households having a smart meter data which generates and reports the consumption values to the server. For centralized learning, a machine learning model is designed with the data collected from smart meters at the server. So each smart meter data has its own data historically to be used for training the machine learning model, and the data collection is performed in a central server, and the training process is performed online. And once we train the model, that can be used in real time, and the trained machine learning model can take the smart meter data and then forecasting the next time steps for each smart meter data individually. And here, Grid Edge is only tasked to generate the data. And of course, the machine learning model can benefit from the data collected from the different smart meters. And of course, here we do not consider the privacy because we are just transmitting the data to the server. So this is just an overview of how the centralized learning is implemented. And when it's in centralized learning, the training and the processing the data is performed in the server or the cloud, right? And when it comes to the localized learning, the computation power is brought to the edge of the network to the smart meters. Even though the smart meters are able to communicate with the system operator, they do not have the ability to perform like advanced computing. Therefore, for the localized approach and for the federated learning, for the privacy preserving as well, and smart meters are assumed to have computing capabilities. And if this computational capability is also based on artificial intelligence, it can also be named as the edge intelligence or edge AI. And in this localized learning framework, the server doesn't have any responsibility as all the processing is performed at the grid edge at the smart meter level. So as you can see here, each house has its own local data and also has its own local model that where the local training is performed, and in the real time, they all work in a standalone mode. So, yeah. And here we assume that each smart meter is equipped with a computing unit, and each model is trained with its own local data. And during the training or inference stage, we don't need to do any communicating with any other entity. It's completely local. And here, Grid Edge is tasked to generate the data and now process the data as well to extract the output. Here, we can say that the privacy is, considered and protected as we are not sharing any information with others. So now we have look at the details for centralized learning and localized learning. On one side, centralized learning can benefit from the vast amount of data collected from different smart meters. However, privacy is not a consideration. On the other hand, localized learning can protect the privacy as we are not sharing any information with others. However, localized learning might suffer from lack of data in a single smart meter data, right? So can we just utilize the data from different smart meters, and at the same time, can we consider the privacy concerns? We can actually do it by using the privacy preserving techniques, which can be mainly clustered in the four main techniques. And the first one is the data anonymization. that could be used to blur the connection between the data and sensitive information to avoid, identity disclosure. And basic methods included generalization, swapping, and masking. The second part is the encryption tools. The development of, modern cryptology has provided new opportunities for privacy protection for encryption tools, and standard techniques include secret sharing schemes, homomorphic encryption, and secure multipart computation. The third type is the differential privacy, where we add some synthesized noise from the standard distribution to the data set, and then privacy can be guaranteed from a statistical perspective, while reliable inferences still can be made on the noise data set. And the last is the privacy preserving learning frameworks, where we can see that federated learning, gossip learning, and split learning are the types of this section. And then we will be analyzing the federated learning and split learning for the smart meter load forecasting problem. And then we will be talking about the federated learning first. So federated learning first proposed by the Google researchers, and it's a distributed deep learning framework. It actually enables multiple participants to collaboratively train a machine learning model by only exchanging the model parameters and keeping the data local so that we can protect the privacy. And there are two main components: the client, that can also be defined as an edge, and the server. The edge has to be, with the edge computing capability. And the edge is also responsible for performing the local training, communicating with the server back and forth during the training process. And the decision or the output based on the defined problem is taken at the edge by the clients, not in the server. So it's a decentralized framework. And the server needs to be trustworthy because it's responsible for aggregating the model parameters and updating the global model. And the server is only acting in the training stage, but doesn't take any role in inference stage. So if you look at the details about how we do the training process within the federated learning, this is one type of federated learning, which is called federated, averaging. What we need to do is we need to first initialize a machine learning model in the server side, and then this model needs to be sent to each clients where we are going to have the computing unit. And then in this step 3, each computing unit trains this machine learning model with its own local data. And then therefore, we are not sending any data to the server. And then training is performed for a certain number of epoch based on the mini batches. And the local patterns, relationships, or the features are obtained during this local training. And once we train the local models, we get some parameters, right? The model parameters. In this version of the federated learning, we are sending the weights that we obtain after the local training back to the server. And then the server receives these parameters and aggregate them, weighted average based on the number of samples that they have in each client. And then we create a global model. And then the global model is sent back to the clients. So this is a one single communication round. And once they receive the global model, they do again the local training and then obtain the new weights and send back to the server. This is how we do the, collaborative training in the federated learning. And once the training is completed, once we reach a satisfactory performance, basically the server doesn't take any role, and we only use the computing capabilities in each client. The second version of the federated learning is federated stochastic gradient descent. In this one is slightly different. The way that we are training the model is slightly different. Rather than the weights, we are sharing the gradients with the server, and the global model is updated based on the aggregated gradients. But the rest of the training part is more or less the same. And as I said, the training stage requires communication between the server and the clients. But when it comes to the inference stage, the server doesn't take any role. So each global model runs with its respective local model, and we can get the output from each client. And there are two types of, actually five types of federated learning can be clustered based on the types of participants and types of data. So regarding the types of participants, if we have the many number of devices or the sensors, measurement devices, this is generally defined as cross-device federated learning. But if we have less number of institution, with a larger number of samples, such as system operators or the part of the network, this can be defined as a cross-silo federated learning. And regarding the type of the data, if we have the same feature set in each client, then this is called horizontal federated learning. But if we have the different features corresponding to the same samples, then this fits to the vertical federated learning framework. But if we have different features and samples in different institutions, then it needs to be, and then it defines as a federated transfer learning. Of course, the horizontal, vertical, and the transformer learning, the way that we train and apply is different than each other, and the design requirement is different from each other based on the data type that we have in each client. And from the perspective of smart grid, these clients can be a DSO or TSO. It can be a substation. It can be a part of the network. It can be a single device such as PMU, waveform, or event recorder. And it can be defined as a wind turbine or wind farm. And it can be designed as an EV or charging station, or it can be designed, as we did here, as smart meter data itself. And the server can be a trustworthy entity, which can be the system operator or data owner, stakeholder, or entity based on. And the next framework is the split learning framework. This is proposed by the MIT researchers, and it's also a distributed deep learning framework. The idea here is a little bit different from the federated framework. It actually splits a machine learning model into at least two components, and allocated these two components to the edge and the server. And it enables collaborative learning without sharing the raw data. And it also enables a flexible split options for different applications. And we will see the details in the next ones. So normally in a centralized way or in a localized learning, what we do is we fed the data to a machine learning model. And then we do the forward propagation through the layers. And then we get the output. And with the label we have, we are calculating the loss. And then based on the loss, we are calculating the gradients and updating the model parameters through the backward propagation. So this is generally what we do when we train a machine learning model. But when it comes to the split learning, we split the model into two sections, and then the first side of the model is allocated to the edge side, and the last part of the model is allocated to the cloud side. This model is also called edge and cloud collaboration. So how are we going to perform the training? This time we do the forward propagation with the edge side models and until the split layers. And once we come to the split layer here, and we obtain some outputs from this part of the model, right? And this is also called intermediate results, intermediate features, or smashed data. And this data needs to be sent to the server. And then so that the server can continue the forward propagation and can obtain the output so that we can calculate the loss and start back propagation. And then what we get is gradients, and the gradients needs to be sent back to the edge side so that we can complete the one iteration. So here in this model, we are not sharing the raw data, rather we are sending the intermediate results, which can protect the privacy. So during the training stage, we are sharing the intermediate results and the gradients. But when it comes to the inference stage, we don't need to have the gradients, only the intermediate results are shared with the server. Of course, the previous one was only, like here we have only two clients, right? The edge and the cloud. But what if we want to have multiple participants in this architecture? So this is how it looks like. Like each client, the client can be the smart meter data, or based on your problem, it can be a larger entity as well. Each client has its own data and has its own edge site model. And again, we need to do the forward pass in parallel for all models. And then we need to send the intermediate results. Then the server aggregate this information and then continue forward pass. We get the output, calculate the loss, and based on the loss, we calculate the gradient, and then we do the forward pass, and then we are sharing back the gradients to each clients. And this is how we do the training in a collaborative way with the split learning when we have multiple participants. And of course, here the important part is that this architecture, we get the output at the server side, right? And if you would like to get the output at the client side, the architecture of this framework should be changed accordingly. Now we will see the next architecture and the last one, where we can get the output from the client, at the client level. Yeah, so this is the last configuration for the split learning. And this version is called split learning in a U-shaped configuration. So the machine learning here needs to be split into 3 sections by 2 split layers. And the parts of the model can be named as a, head part of the model, body part of the model, and the tail part of the model. The head and the tail parts of the model are allocated to the client, is the first and the last part, and the body part is allocated to the server part in this specific configuration. So the same information sharing principle as we have discussed in the previous layer is also valid here. Each head part here, first do the forward propagation and send it to the server, and then server aggregate process, and then send back this extracted intermediate features back to the tail parts, so that we can get the output at each grid edge or the client. So this is the type of the split learning that you can get the output at the client side. So basically, information exchange. In the training stage, we are exchanging the intermediate features and gradients. When it comes to the real-time operation, we only need to exchange the intermediate features between the client and the server. As the raw data and the labels are kept at the edge, this algorithm is one of the privacy preserving techniques. And before moving to the application of these algorithms to the load forecasting, smart meter load forecasting, we can take a 10 to 15 minutes break, and then we can continue. Or if you have any question, I can also I'm happy to answer your questions as well. Thank you for listening. So we will be continuing with the application of the methods that we have discussed. And the first one is going to be the federated learning. And then, like as a recap, for the application of federated learning to smart meter load forecasting, we have now 2 components, the clients and the server, as we discussed before. So in this case, the clients is going to be the households with smart meters equipped with the edge computing capabilities, and which is responsible for generating the consumption data and performing local training of the machine learning model during the training, and communicating with the server, which can be the weights or gradients, and which is also responsible for obtaining the output, giving the output. And the server is so the server should be a trustworthy entity that can be designed the system operator in this case, and which is mainly responsible for aggregating the parameters which is sent to the server and updating the model based on the received parameters. And this is how it looks during the training stage. These edge computing units in the smart meters need to collaborate with the server side. When it comes to the inference stage, we do not need to we do not need to communicate with the server, so they can actually work based on the local data and get their output. For the split learning, again, we have the same components, but the way that we operate it is different. So the clients, again, are the households with smart meters, again, equipped with edge computing capability. Again, the clients are generating the consumption data, but this time they are extracting the intermediate features and they are sending it to the server side, and also the clients, of course, getting the output at the edge side. And here, the server now is actively taking part in both training and inference stages, and it's responsible for processing the collected data from the edge side models. And now we have actually a part of the machine learning running in the server compared to the federated learning. And the server is responsible for sending and receiving the intermediate features and gradients during the training stage. So this is how it looks like for the inference stage. We have the head and the tail parts located at the edge computing at the grid edge side, and the body part is located at the server side. And then they are extracting the features and then sending it to the body part, and it is processed by the body model, and then this obtained information is sent back to the tail so that we can get the output at the grid edge sides. So there are some assumptions that we have made before that I would like to tell you before giving the results. So here smart meters are assumed to have the edge computing capabilities, and smart meters are able to store enough historical data to train the deep learning model. And here we omit the synchronization problems and missing data cases, and we haven't modeled any communication network, and only the vanilla frameworks are considered, and the implementation is done in Python. And here we are using the privacy is protected. The term the privacy is protected due to the fact that the raw data is kept at the edge, as we are sharing the the weights, gradients, or intermediate features. However, there are some further studies where additional methods are performed, such as encryption or the differential privacy on top of the federated learning or split learning frameworks to provide further privacy protection. And for this specific problem, this table gives basic information of several open load data sets where reporting rates changes from 15 minutes to an hour, and the number of smart meters can be found up to 6,000, and a range of historical data length changing from 1 year to a couple of years can be found among them. And the data sets are also from different locations such as UK, Austria, and US. So we have picked the first one here from the Irish data set, which is a smart metering project took place during 2009 and 10 with over 5,000 Irish homes. And for this specific problem, we have selected 25 smart meters to test the effectiveness of the algorithms and comparison. And we also perform a clustering to get the similar patterns among the smart meters. And 1 year of data is used for each smart meter data. First 9 months is used for the training, and the last 3 months is used to test the data. So how do we design the data set format? So if we just assume this vector is it represents a day consumption values from a smart meter data, and if we want to predict the next hour consumption based on the last or the past 4 observations, this is what we do. We actually take the 4 past samples as our measurements or observations, and we are taking the next one as our label. So this is how we create a sample, basically. And then we take the next 4, from second to fifth as our second sample, and the 6th one is going to be our label or the ground truth. And then we are doing like a sliding windows for the whole data that we have. And in this way, we are creating thousands of samples from different smart meters. And then we are also getting our labels. And then with the machine learning, we are mapping these two so that we can learn the, relationship between these two. And then of course, this, the data set that we have created is shuffled and then divided into training and test sets. And this is done for all the cases. For the centralized learning, local learning, or federated and split learning, this has to be done in this way. So for the settings, the aim here is to forecast the next time step, the next hour consumption value, And we also investigated how the effect of the number of smart meters is affecting the results. And we have also investigated how the different length of historical data from 9 months to 3 months, is affecting the results. And we have also compared the number of the previous time steps that the forecasting is performed on. For example, we take the previous 6, 12, 18, and 24 observations, and we do the forecasting based on this number of observations. And also we have compared 4 frameworks that we have discussed: local, centralized, federated learning, and split learning. And as a base model, we have used a deep learning neural network model, which consists of 9 layers, and the mean square error is used as evaluation metric. For the local, centralized, and federated learning, we are actually using the full model as part of as a base model. But when it comes to the split learning framework, as we have discussed, we need to split the model, right? And we are using the first 2 and the last 2 as head and tail models respectively, and the rest 5 in the middle is used in the server as the body part. And here we have compared the performance of these 4 frameworks against different number of clients ranging from 5 to 25, and the graph shows the individual client performances. So each client basically represents a smart meter here, and the colors represent the performance of different learning frameworks, which are the local, federated, split, and centralized respectively. And what we see is that almost for all smart meters, the machine learning models that are trained under the federated learning framework outperforms the others. And even though the machine learning model deployed at the smart meter number 3 shows that the centralized learning and federated learning are so close to each other, as you know, and as we discussed, centralized learning don't consider the privacy limitation, while the federated learning does. And for split learning, for the smart meter number 3 and the 4, it shows like better performance than the local learning, however, worse than that of the federated learning. So the local and the split are the worst, and the federated and the centralized learning are showing the best results among all. And if we increase the number of clients to 25, and with these results, for each framework, more or less the same results are also obtained. So federated learning outperforms the others for most of the smart meters, for the most of the clients. And the performance of split learning and the local learning frameworks are changing from client to client. And like sometimes the local is performing better, and sometimes the split learning is better than the local one. Therefore, it is hard to make a comparison from this graph. But centralized learning outperforms the federated learning at some smart meters. However, as it was stated, the centralized learning is not considering the privacy concerns. So if we look at the mean values so that we can compare from an overall perspective, and this graph shows the mean values of the clients for different number of clients from 5 to 25. And we see that the federated learning represented by the orange color performing the best when the number of clients are set to 5, 10, and 15. And when it is set to 20 and 25, centralized learning outperforms the others. And even though the split learning requires a lot of communication and competing, it's not able to show a distinct performance compared to the local learning framework and the others. Of course, it's also important to remind you that we have used like a basic deep learning model and didn't consider a specific model development process for each framework. And maybe with different strategies and updates, maybe different, base model design, the comparison, and of course, should be evaluated again as, their performances might change. And here the effect of the number of previous observations used as input is evaluated. So we do the forecasting based on the previous 6 time steps, or 12 observations, or 18, or 24. And when the number of clients are set to 10, for the graph on the left, we see that the performances are getting worse once the input length is extended from 6 to 18. However, once the input length is set to 24, the performance reached to a point where the federated learning and split learning reach their highest performance. And the performance of the centralized and localized learning frameworks also increases once the input length is set to 24. However, their highest performance is recorded when the input length is set to 6. And when we increase the number of clients, to 25 on the right, we do see a similar pattern for local, centralized, and split learning frameworks. However, the performance of federated learning is affected negatively this time when the input length is, set to higher number when there are 25 clients. And as a result, these parameters are kind of hyperparameters and affecting the performance of the frameworks. Therefore, a proper analysis is required to find the best hyperparameters for the given cases. And moreover, there are many studies investigating the trends in these public data sets that can also be a good starting point to arrange these parameters as well. And for this one, we have compared different training set lengths, which are set to 3 months, 6 months, 9 months, respectively. It can be seen on the x-axis. And the test data are kept as the same as 3 months in each cases. We also have done it for different number of clients and from 5 to 25. The analysis showed that the length of the training data is significantly affecting the performance of each framework, irrespective of the number of clients, ranging from 5 to 25. And what we see here, when the number of clients are set to 5 or 25 each case, the longer training data set length historically improved the performance of all frameworks. And if we read the graphs in a vertical way, we can also compare their performance under different training dataset length. And in most cases, the federated learning and the centralized learning kept their position at the top and compared to the local and split learning frameworks. So, and this is the last graphs that we have as a result. And we can also see the overall comparison. And this table shows an overall comparison regarding the type of information required to exchange between the edge and the server. So for the centralized learning, we are sending the raw measurements, but not caring the privacy. For the localized, we are not sharing anything with anyone. And this is why we are getting the worse performance. Federated learning is exchanging the model parameters and can deal with the privacy concerns, and it's also outperforming the other methods. Split learning is not sharing the raw measurements, but changing the gradients and in intermediate feature, and it requires a lot of communication rounds between the client and edge server. However, it doesn't actually provide in these cases high performances. And for the communication requirements, localized learning, as we discussed, doesn't require any collaboration between the server and the edge during the training and inference. Federated learning needs to collaborate with the server during the training stage, but it works, by itself during the inference stage. However, split learning requires communication both during the training stage and inference stage. So when we look at the challenges, I think scalability is a challenge because when the number of clients are increasing for the federated learning and split learning, it's a little bit problem regarding the requirements regarding the computation. Then you need to have a strong computer to deal with the maybe thousands of smart meters. And heterogeneous data is also another problem when it comes to these privacy preserving problems, because once you have very different patterns in each smart meter, it can affect the training performance. So you need to be careful with the heterogeneous data, and then you need to design accordingly your algorithms. So the vanilla frameworks might fail when you have very different characteristics. And of course, we have basically split the model into 3 sections for the U-shaped configuration. but you might have very different configurations with different specifications with different models. So this is also a challenge. It needs to be designed based on the problem, the data, the temporal and the spatial information that we have in the grid. And of course, some studies suggest that additional studies are required to further protect the privacy of the data, like combining the differential privacy encryption and these privacy preserving techniques. So this can be further investigated in later for further research. So this is going to be my last slide. And thank you so much for listening. This is my email, so you can just reach me out through the email or my LinkedIn research Gate profiles. And thank you so much for listening this presentation. And if you have any question, I am happy to answer them.
Thank you very much, mate, for a good presentation. We are taking the first question from Kuta.
Hi, Mert. Can you hear me?
Yes, hi, Kutay.
Great. So thank you for the presentation. It's a great work. So I have a couple of questions about the results. Actually, like you showed some RMSE values, right? If we can go back to those, like with the bar graphs one, your client one, two, yes, this kind of. So like I see RMSE is like something like 0.4, 0.3, and I mean, at first glance, I assume these are after normalization, right? Like it's not like the kilowatt hour kind of values. Otherwise,
Yep, it's based on the normalized values. Yeah, I didn't mention it. Sorry. Yeah.
Yeah. Okay. Otherwise, I mean, if they are kilowatt hours, they are pretty much zero, right?
Yeah.
So, and maybe can you give some intuition about, like federated learning is better than, why it is better than centralized? Because, when you think about it, centralized should have everything, right? So I would at least expect as good, if not better, right? So if I look at this, I say, okay, if I also have a data set and I want to train a machine learning model, and it's a centralized thing, right? It's in my computer and it's not related to smart meters, etc. But this graph shows me that, okay, I should just create some random clients and I have to federate my, distribute my data and you run a federated learning, and it's gonna be better for my whatever machine learning task. So it looks a little bit counterintuitive to me. So I think there shouldn't there be some sort of trade-off between, I don't know, like the federated learning and like the performance? Because if federated learning works that good, why don't we all right now use federated learning for all of our machine learning tasks?
Yep, you are completely right. Yeah, as we have randomly select these 5, 10, and the 15 clients among these like thousands of smart meters, it's also, yeah, you are completely right. It's a little bit random until this point, but when I increase the number after like 15 for the 20 and 25, the centralized learning is giving like better performance than the federated learning. So I guess for this first part, it's I think there are a little bit randoms. Maybe I need to do like thousands of trials and I need to take the mean and variance. Maybe we can reach to a better solution for this comparison. I think this is what needs to be done for a fair comparison.
Okay, thank you very much.
Yeah, because as you said, the centralized learning have all the data, so it should perform better. And also after this point, for the 20 and 25, centralized learning is performing better than the federated learning. But as we said, it's not considering the privacy, and the federated learning is close to the centralized and is better than the local and than the split one.
I think, I mean, there's also like for 5 clients, you have less data, of course, right? So when you have more data, maybe in the for the centralized, it's more beneficial for it. Maybe can we say like, okay, if we have less data in case of 5 clients, let's say, federated learning is sort of better to avoid sort of overfitting or something like that?
Yep. I agree completely.
Yeah. Thank you.
You're welcome. Thank you for the question.
Thank you very much. We are having a second question from Angea.
Thank you very much for the presentation, Matt. I have a question regarding the data set requirement. How much data you would train such a model? Yeah, and another question is whether how scalable such a model is when you have a distribution grid with maybe thousands of feeders where you have to estimate.
Yeah, for these models we have used, and like historically we have used a year data for each smart meter data, and then we have considered like 25. Like as I have been doing like different studies, I just kept this number small, but I think like my computer can handle maybe around 100. And of course, if it is like local and centralized, we can increase the number. But when it comes to the split learning and then the federated, specifically the split learning, as we are doing this gradient calculation like separately, and then it requires a lot of GPU, and this is the problem for me. But with my with the pieces that we are using, I am able to like deal with like up to 100 smart meters. But for the more, I mean, we need to have like more computing facilities, I guess.
Going to resume at